What specific problem does the proposed method aim to solve according to the paper?
The proposed method aims to solve the problem of generating extensive formal proof data by auto-formalizing informal mathematical problems, filtering out low-quality statements, and proving the correctness of these statements using a large language model, LLM, and a formal verifier. The method addresses the challenges of crafting formal proofs manually, the limited availability of parallel corpus for training LLM-based automated theorem provers, and the inefficiency of existing methods in handling the vast search spaces required for complex theorems. By automating the process of translating high school and undergraduate level mathematical competition problems into formal statements, filtering out simplistic or invalid statements, and proving the correctness of the generated proofs, the method aims to enhance both the scalability and quality of synthetic data for automated theorem proving.
How does the proposed method work to generate extensive lean for-proof data from informal mathematical problems? Illustrate step by step.
The proposed method works to generate extensive lean for-proof data from informal mathematical problems through a systematic approach. 1. Auto-formalization of informal math problems. The method begins by auto-formalizing high school and undergraduate level mathematical competition problems into formal statements. This involves translating the natural language descriptions of math problems into formal statements in Lean 4 using a structured approach. 2. Quality filtering. The auto-formalized statements undergo quality filtering to ensure high standards. This step involves scoring the statements based on quality criteria and excluding overly simplistic or invalid statements. The model is guided to classify statements as excellent, good, above average, fair, or poor, with fair or poor statements being excluded. 3. Hypothesis rejection. To eliminate statements with inconsistent hypotheses, a hypothesis rejection method is implemented. The DeepSeek-Prover model attempts to prove the formal statements with false as the conclusion. If a successful proof is achieved, indicating an invalid hypothesis, the statement is excluded from the dataset. 4. Statement proving. After filtering, the high-quality formal statements are subjected to proof search using the DeepSeek-Prover model. Instead of brute force attempts, the method leverages logical symmetry by concurrently proving both the original statements and their negations. The search terminates as soon as a valid proof is found for either, enhancing proof synthesis efficiency. 5. Iterative enhancement. The model is continuously fine-tuned and improved with newly generated data in an iterative process. The refined model is then used for subsequent auto-formalization iterations. This iterative approach ensures that the DeepSeek-Prover consistently enhances its performance, leading to higher quality theorem-proof pairs with each cycle. By following these steps of auto-formalization, quality filtering, hypothesis rejection, statement proving, and iterative enhancement, the method successfully generates extensive lean for-proof data from informal mathematical problems, ultimately improving the scalability and quality of synthetic data for automated theorem proving.
What are the theoretical or practical benefits of utilizing auto-formalization for generating formal proof data?
The theoretical benefits of utilizing auto-formalization for generating formal proof data lie in the ability to leverage natural language math problems to create a vast repository of formal statements. This approach allows for the synthesis of high-quality formal statements from informal math problems, enhancing the scalability and quality of synthetic data. By auto-formalizing these informal mathematical problems, a substantial corpus of formal statements can be generated, enabling the training of models like DeepSeek-Prover to improve theorem-proving capabilities in large language models, LLMs. Additionally, auto-formalization facilitates the creation of formal proofs at a much larger scale, boosting the performance of neural provers by providing a diverse and extensive dataset for training. Practically, auto-formalization streamlines the process of generating formal proof data by automating the translation of natural language descriptions into formal statements that can be verified by proof assistants. This method not only accelerates the proof generation process, but also ensures the efficiency and accuracy of the generated proofs by filtering out low-quality statements and identifying inconsistencies in hypotheses. Ultimately, auto-formalization contributes to advancing automated theorem proving by providing a robust foundation of formal statements and proofs, fostering further research and development in the field.
How are the formal statements filtered for quality in the proposed method?
The formal statements are filtered for quality in the proposed method through a two-step process. Firstly, a scoring model is utilized to evaluate the quality of each formal statement based on criteria such as content and coherence. The model classifies statements into categories like excellent, good, above average, fair, or poor. Statements rated as fair or poor are then excluded from the dataset. Secondly, a hypothesis rejection strategy is implemented to identify and eliminate formal statements with inconsistent or false hypotheses. The DeepSeek-Prover model attempts to prove the formal statement with false as the conclusion. If a successful proof is achieved, indicating an invalid hypothesis, the statement is excluded from the dataset. This dual strategy of model scoring and hypothesis rejection ensures that only high-quality formal statements, free from invalid hypotheses, are retained for further proof synthesis, resulting in a refined set of high-quality formal statements for theorem proving.
What were the main results achieved with the proposed method in terms of accuracy on different benchmarks?
The main results achieved with the proposed method in terms of accuracy on different benchmarks were as follows. On the mini F2F benchmark, the DeepSeek-Prover outperformed other methods with cumulative scores of 60. 2% on mini F2F valid and 52. 0% on mini F2F test, surpassing GPT-4 at 25. 41% and 22.95% respectively. Even the best tree search method, Hypertree Proof Search, achieved only up to 58. 6% on mini F2F valid, and 41.0% on mini F2F test. Additionally, on the FIMO benchmark, the method successfully proved 4 theorems with 100 attempts per theorem, while GPT-4 failed to prove any. By increasing the number of attempts per theorem to 4,096, an additional theorem was successfully proved. These results demonstrate the effectiveness of the proposed method in achieving high accuracy in theorem-proving tasks on different benchmarks, showcasing its superiority over existing methods like GPT-4 and tree search approaches.
What future work do the authors suggest in the paper for improving the method?
The authors suggest future work in the paper for improving the method by exploring the integration of domain-specific knowledge to enhance the quality of auto-formalized statements further. Additionally, they propose investigating the incorporation of more advanced search strategies to optimize the proof synthesis process. Furthermore, the authors recommend delving into the development of techniques to handle more diverse mathematical topics beyond algebra and number theory, such as geometry, combinatorics, and statistics. They also highlight the potential for refining the iterative enhancement process to achieve even higher quality theorem-proof pairs. Lastly, the authors hint at the possibility of exploring ways to scale up the dataset generation process to create an even larger corpus of formal mathematical proofs for training models.